The problem 8 of the test 3 review. This problem is the longest problem probably in that test 3 review. Lots of stuff to analyze, lots of stuff to answer. So let's get started. It says 10 moles of an ideal gas at a temperature of 30 Celsius and volume 500 liters is allowed to expand isobarically. Okay, so you have a process taking place here, a thermodynamic process. Isobaric means constant pressure. So it's expanding under constant pressure to a volume of 1200 liters, right? A, it says, what is the pressure in the gas? B, what is the final temperature of the gas? C, what is the work done by the gas? What is the change in its internal energy? E, what is the heat flow into the gas? And then the question says, what would be the answers if instead of being isobaric, so the same process took place, but instead of being isobarically done, you were given this information. You were told 80 kilojoules of heat are absorbed by the gas while it's expanding. So 80 kilojoules of heat are absorbed by the gas, and its final temperature was already given to you as 400 Celsius. So let's see what would be the differences of those two. Okay, so let's start. So we already have the number of moles. Let's write the pieces of information here. 10 moles. We have the initial volume, 500 liters. We have the final volume is 1200 liters. So we could kind of erase this top portion. And we also have the initial temperature, which is 30 Celsius. Right? With this kind of problem, we're always going to be utilizing either the combination of either the ideal gas law, PV equals nRT, or nKT, and we're going to be utilizing the first law of thermodynamics, heat into a gas is equal to change in internal energy of gas plus work done by gas. And on top of that, it is also a good idea to write PV diagrams for the gas and also to draw what the gas is actually doing in the chamber. Okay? So the chamber is something like this. Initial volume of the gas is 500 liters. The gas is expanding. So the gas is expanding under constant pressure. Now, why would the gas expand under constant pressure? Heat is coming in. Somebody, maybe the burners are on here, okay? Somebody is putting in heat. So I'll just put some picture to visualize the flame. So flame is coming in, heat is coming in. When the heat comes in, the temperature is going to go up, right? The temperature is going to go up. If you had the piston locked, what would happen? The temperature would go up, the pressure would go up, the volume would stay constant, right? So it would really build up a lot of pressure. But since the piston is free to move, your heat is coming in, the gas is allowed to expand, the gas does work against the piston, and the piston expands this way. The final volume of the gas, so the piston goes all the way up. The final volume of the gas is 1200 liters. And then the final temperature, we don't know. So we want to know what is the pressure in the gas. The pressure stays constant. What is the final temperature? And what is the work done? And so on and so forth. Okay? What does the PV diagram of this look like? Okay? So we can erase the questions here, some of the beginning questions. So the PV diagram, again, the initial volume is 500. This is in liters. The pressure, we can either express it in atmospheres or pascals, but it's probably better to express it in pascals. And as a matter of fact, it is better to express the volume in meter cubed. Right? Just so that we can be more in the metric unit system. Well, how would we convert from 500 liters if the initial volume is 500 liter, we can say what? 1,000 liters is 1 meter cubed. Okay, I've used this in one of the earlier problems. So what is that equal to? That's equal to half a liter, half a meter cubed, right? So we put here 0.5 meter cubed. So the initial pressure we don't know. And 1,200 liters would be what? Well, divide that by 1,000, 1.2 liters, right? So the volume is more than doubling, right? And it's taking place isobarically. So it's basically going this way. The area under the PV diagram is the work done by the gas, always. So it's this area right here. Okay? So here we go. Let's go ahead and answer some of these questions. What's the pressure of the gas? PV equals nRT. The pressure, we don't know. The volume is 0.5. The number of moles is 10, 8.314. Then we convert the temperature to Kelvin. Remember, the original temperature was 30 Celsius. So we convert that to Kelvin, 273.15 plus 30. So let's see what that gives us. 10 divided by a half, that's 20 times 8.314 times 30 plus 273, that's 303. 303.15. That gives us 50,407.78 pascals. That is the answer in terms of the pressure. So that would be over here 50,000. So we could say 50 kilopascal just for short. 50 kilopascal. How many atmospheres would that be? Well, we know 101,300 pascals. So if we divide that by 101,300, that's actually about a half an atmosphere, 0.49. So approximately 0.5 atmospheres. So the pressure in that chamber is less than atmospheric pressure. Okay. Okay, so now what's the second question? Well, we want to know what is the final temperature, right? Well, what do we use? The ideal gas law, right? The pressure stays constant, so the volume and the temperature are linearly proportional to each other, right? So we could say V is proportional to T, right? So V1 over V2 is equal to T1 over T2, right? Since volume over temperature is constant, so we could say V1 over V2, or we could say V1 over T1 is equal to V2 over T2. Well, that's the same thing as this. V2 can come down here, T1 can go over there. So either way, we can, same argument, right? So we're trying to look for T2. So T2 is equal to T1 V2 over V1. Okay, so what was T1? Okay, so what was T1 here? 303.15. Okay, we want to make sure we have that in Kelvin, right? So we can get the answer here in Kelvin. So 303.15 Kelvin. V2 is equal to 1.2. V1 is equal to 0.5. What do we get here? 303.15 times 1.2 divided by 0.5. So 727. T2 is going to be 727.56 Kelvin. So it went all the way from 303 Kelvin all the way to 727 Kelvin. Now we can scale back down to Celsius, subtract 273.15, 454.41 Celsius. So T2, 454.41 Celsius. So in Celsius, we went all the way from 30 Celsius all the way to 454 Celsius. So it's going to be quite hot. Okay, we put in a lot of heat in there. So now we know the final temperature, we know the final volume, we know the pressure.